Hi, welcome to part 3 of the series Deriving Euler's Number. Today's agenda is to find the derivatives of exponentials and logarithms. In the previous videos of this video series, we have only worked on prerequisites to deriving Euler's number, but today we actually start the main derivation. Okay. So one thing to let you know about is that I'm going to assume that you know about the chain rule in derivatives. In case you're not aware of this topic, or if it has been a long time since you've touched this topic, I would recommend revising it. Some sources that I use are Khan Academy videos and Gilbert Strang's book on calculus. These are two sources you could use to revise this concept or learn about this concept. In case you would like me to create a separate video on explaining chain rule, please let me know and I'll create it. Okay, so for now, let's start off with our first topic for today, which is finding the derivative of exponentials. Now, we had discussed exponentials in the first video of this video series. An exponential is just an expression of this kind, like y is equal to b raised to x, right? Where x is the exponent, b is the base. Okay, so now what we are going to do is we're going to use the expression of an exponential with the fundamental theorem of calculus, which you can see over here. Sorry to create a mark over that. I'm just going to undo that. Okay. So this is the equation we discussed in the previous two videos. I talked about it in more detail in part 2 of this series. Now, if you look over here, we can see that y is equal to b raised to x. This means that when we find the derivative of y, we could write it in this way. So dy by dx is equal to limit of h tends to 0 with b raised to x plus h minus b raised to x divided by h. Now if you notice over here, b raised to x plus h can be converted to b raised to x times b raised to h, which is a property we talked about in the first video. So let's rewrite it in that form. Limit of h tends to 0, b raised to x times b raised to h minus b raised to x divided by h. Now let's take b raised to x as common. Okay, so we say again limit h tends to 0, b raised to x times b raised to h minus 1 divided by h. Now if you notice over here, this term in the parentheses is actually a constant because it does not have x in it. It's b raised to h minus 1 divided by h, where h tends to 0. H is a constant. So what we are going to do is we're going to convert this entire term to just one constant variable, and hence saying that this is equal to c times b raised to x. So we have represented limit of h tends to 0, b raised to h minus 1 divided by h as c. Now have a look at this equation. This is a very cool equation. It says that dy by dx, or d by dx of b raised to x is equal to c times b raised to x, which is technically equal to c times y. So this means that the change in y is proportional to y itself. Now let's try and understand this in more detail. Okay, let's say that the expression is this: y is equal to 2 raised to x. Now when x is equal to 0, you have 2 raised to 0, which is equal to 1. When x is equal to 1, you get 2 raised to 1, which is equal to 2. When x is equal to 2, you have 2 raised to 2, which is equal to 4. And then 3, where it's 8, and so on. And can you see, as b raised to x is changing, or as x itself is changing by 1 point, the change in x, the change is also becoming bigger, right? So if you see over here, earlier the change was 2. Sorry, the change was 1. Then here the change was 2. Then the change was 4. Can you see that the change is also very similar to how the actual y is changing? So the change in y is the same as the y values, which is a very interesting concept. To help you understand it better, I have created this graph over here on the top, which basically is the graph of 2 raised to x versus the values of x. So you can see that as x's value increases, so does this graph's change. Do you see? So this is called the slope. And you can see that the change in the y values, or the y-axis values, or 2 raised to x values, are also increasing as x increases. And you can see the steep rise over here as x keeps increasing. Okay, so this is what this main equation means, that dy by dx is equal to c times y, that the change in y is proportionate to the value of y itself. Okay, so now we come to this point, and I'm going to talk about one more thing over here, that, once again, let me write it over here. Okay, so now we know that y is equal to b raised to x, right? That also means that log of y with the base b is equal to x. This means that the derivative of log of by by dy would be equal to dx by dy. So should that mean that actually dx by dy, or the derivative of the logarithm by the derivative of the logarithm, is just equal to 1 by cy, or 1 by c raised to c times b raised to x? Could be. Let's try and prove this. And this is where you see the occurrence of inverse functions. So you see, we are saying that the derivative of a logarithm is just the inverse of the derivative of an exponential. So this is how I'm going to lay out the next part of this video. Okay, now let's go to the next topic, which is actually proving the fact that the derivative of a logarithm is 1 by c times b raised to x. Okay. So we'll start off with this. I'm going to just rewrite that equation we talked about and say that the derivative of the logarithm yb by dx is equal to 1 by c times y, which is equal to 1 by c times b raised to x. Okay. Now the way we are going to derive this is going to be slightly different. Okay. So let's start off. First of all, we could say, now this is where I'm going to be using the chain rule. So you'll only be able to understand this derivation if you fully understand the chain rule. Okay. So what we are going to do is, we are going to look at log of y with the base b in two ways. Now, once again, I'm just going to write this down. Okay. I'm going to write it as b raised to x because that will start making more sense. Okay. Now what we are going to do is, instead of saying log of y with the base b, or log of b raised to x with the base b, and deriving it by dy or d of b raised to x, we're going to derive the entire thing by dx instead. Now that is why the chain rule is applied over here, because we are not saying log of by by dy. Once again, this is my mistake. This should be dy over here. My mistake. Okay. So instead we're going to say dx. Therefore, based on the chain rule, we could say that this is equal to, first of all, derivative of log b, and here I'm going to write y just for convenience instead of b raised to x, and write dy. And then we're going to derive y itself, which is d of b raised to x derived with dx. Now in the previous part, we just said that the derivative of b raised to x is c times b raised to x. So we could rewrite this in that way. D of log by by dy times c times b raised to x, right? Now this is our first equation. Okay. Now let's have a look at the second part. We're going to change log of b raised to x. So basically log of b raised to x, as we had seen earlier, is equal to x. So you could say that here we're deriving x, which, if you have learnt about derivatives, is just equal to 1. Now you see, equation 1 and equation 2 are equal. Therefore, they can be equated together. And what we are going to write is this. I'm going to write this in pen color so that it's easier to understand. Okay. So now we say this. 1 minute. We're going to say that d of log by coming from equation 1 times c b raised to x is equal to 1. So this means, I'm going to write it on this other side, that the derivative of log of by dy is just equal to 1 by c times b raised to x, which is exactly what we said in the previous part, that because they are inverse functions, the derivative of the logarithm is just dx by dy, which is the inverse of dy by dx. Hence proving what we had talked about earlier. Okay, so this is where I'm going to stop today's video. We are going to use these derivatives in the next video to finally understand why Euler's number is approximately equal to 2.718. Okay, then I hope you have a great week and I'll see you in the next video. Thank you.